Huh?
All right, what?
Maybe.
You have a question for me?
No, I just said, yeah. Yeah. What question do you have, Mark?
Number 11.
Compare size.
On the front?
Yeah.
Okay.
Greasy cake. Yeah. Okay.
So, if you're an engineer,
Exactly.
okay, here's the deal. You always plan for a worst case scenario. Okay? It's like, so you got to figure, okay, when is this elevator going to be most likely to break? So every cable, chain, anything has a breaking point. If you want a cool job, get a job in a factory that tests those, because you have these big hydraulic presses and you just basically pull stuff together until it breaks. It's a cool, you basically get paid to break stuff, okay? It's a cool job to have. So every cable has a breaking point. So then you're the engineer and you go, okay, I know the breaking point of the cable. That's the maximum amount of force that this thing can apply. Then you go, okay, this is going into an elevator. What's a worst case scenario? Worst case scenario is that 20 drunk frat guys decide to get into the elevator, okay? Worst case scenario. On average, excluding beer, each one has a mass of 75 kilograms, okay? So then you can figure out, okay, so what's the total mass of all the drunk frat guys in the elevator? Okay, cool, all right. But then what else do you have to lift up? The elevator itself, okay? So, when you go to accelerate this thing upwards, okay? When you go to accelerate it upward, what's going to be working against you? Gravity, okay? You've got to pay the gravity mafia. So no matter what, if it's an elevator, a helicopter, it doesn't make any difference. The gravity mafia is always present when you're dealing with vertical situations. So you go to this and you set up your chart. Okay, so I got some FAP, I got some FOP, I got some FNET. Now, here's the beauty of every force problem. Every force problem can only go one of two ways. What are the only two ways it can go? No, that's a subset. What are the only two options that I can do with any force problem? One is be at, runs with constant velocity. Constant velocity. The other one is, otherwise known as accelerated motion. Now, when it is accelerated motion, what are my two options? Yeah, that's it. So I basically have either constant velocity or I make it speed up or slow down. That's it. It's a three-trick test, okay? Those are the only three things I can possibly do. And if you have positive velocity and you're speeding up, what do you think the sign of your acceleration is going to be? Oh, let's go with positive, okay? So here's the deal. In a gravitational field, which we're in, your opposing force is always going to be the gravitational force between this object and this strange rock that we're on, okay? That's what's going to happen. So how can you always calculate that gravitational force? What are you going to do? It's the easiest calculation you're going to do.
Mass times gravitational acceleration.
Mass times your gravitational acceleration. Now, in this situation, I would make that negative because that's going to be going down. So you can find this number, okay? What's going to provide the applied force?
The elevator.
The cable that's hooked up to it, right? Okay? The elevator that's hooked up to it. Or excuse me, the cable that's hooked up to the elevator. So I've given you that number. So you're going to know this number and you're going to know this number. Then what can you find? You can find your net force. The net force, and listen to me, listen to me, listen to me, listen to me. It is only net force that is equal to mass times acceleration. Okay, that's it. It is only net force that is equal to mass times acceleration. So once you get that, you're going to know the mass, divide that, boom, there you go. So if all goes well on problem number 11, you should get an answer between 4 and 8 meters per second squared.
Mine is between that, but I feel like it's wrong.
Yeah.
Can you can narrow it down a little bit?
No,
That's a
Say
big
it's a
gap.
closer to 4. How about
Okay,
that?
that's
Say
fair,
it's a
that's
whole
fair.
number.
That's a good one.
It could be a whole number, yes, but it better not be a whole number allowing for significant digits.
It has to be,
See what he says there?
Okay.
but it's a whole
I
number.
like that. Oh.
Yeah. Okay. Now, let's talk about 9 and 10, okay? So on number 9, you're talking about this elevator moving at constant velocity. So what's your net force going to be?
0.
0. Now think about number 10, okay? On number 10, I want it to accelerate upward. So think about this. So, but at first I was just moving this elevator at a constant velocity. But then I want to make it accelerate and make it speed up. So do you think that's going to take more force or less force than just to move it at a constant velocity? Well, intuitively, it's going to take more force. So your answer to number 10 better be bigger than your answer to number 9. Because not only are you holding up the elevator, you're making it accelerate. Okay?
How do you know, like, which way the, or, how the velocity vector, do we have to draw velocity vectors on that?
No.
Okay, alright, that's what.
No. That's why I said just make a free body diagram. That's just forces. Okay. But because of the fact that you've got a positive acceleration, your velocity vectors will be pointing up and getting bigger. But you don't have to draw those.
Okay, so it's fine if we do, just in
If
case
you
it helps
did, yeah,
us.
that's fine.
Okay.
Now, when you get to question number 12 with the helicopter, mathematically, number 12 is identical to number 10. Okay? Because look at number 12. You've got the mass of the helicopter, pretty decent sized helicopter, right? Okay? So here's the deal. If you're just going to make the helicopter hover, how much force do the blades have to apply? Enough to balance out what?
FG.
Yeah, the weight of the ship, okay, the weight of the helicopter. So at a minimum, just to hover, your applied force has to be equal to the weight of the helicopter. So now, again, look what's happening on number 12. I want this thing to accelerate upward. Are you going to apply more force or less force than just the bare minimum?
More.
More, because you're making it accelerate upward, okay? Cool with that. Now let's talk about the Atwood machine problem, okay? In terms of like a conceptual idea. So here's your pulley. You had 200 grams on one side and 220 grams on the other. So here's the basic idea. Is that we're going to set this up and we're going to call this the applied force because this is what this thing is doing. It's dragging this down, right? And I even tell you in the instructions, call this the applied force. Okay? Don't make this difficult. Read the instructions. So what did you get when you took 2.2 or 0.22 kilograms and multiplied that by 9.8? It's 2 point something.
26.
2.16 newtons. Okay? So this is trying to drag this system down with a force of 2.16 newtons. Now, problem is that you've got to drag that 200 gram mass with it. Okay? So not only do you have to drag the 200 gram mass, gravity is trying to pull it down going, oh, don't leave me, right? So even if you like, well, yeah, I know Carson is. So let's say his older brother, which I find this hard to believe, he goes out on a date, okay? And he's got to take, and Harrison has to take you with him, okay? Because you got to babysit, right? You're babysitting, he's going out on a date. So this is like dragging along little brother, right? So what's going to happen to your acceleration because you drag along little brother?
Probably go up.
Well, I'll give you that. That's probably true. But from a pure mass standpoint, it's going to slow it down. It's like, oh, I got to drag along little brother, little sister, whatever the situation may be. Okay. So, because you got to drag along, oh, I know I'm not going to use it. Maybe Ben, okay?
Ben's been dating Nadia for 3
Huh?
years. Ben's been dating
Yeah.
Nadia for 3 years now, so.
Well, I know, but, okay.
Sam,
So,
Sam doesn't have a chance
here's
on his
the
own,
point.
so.
This is dragging along the little sibling, right? You can't accelerate as quickly. So, if you take 0.2, this is going to be 1.96 newtons. So it's this exact same idea. You're trying to drag this thing with an applied force of 2.16 newtons. Gravity is pulling down on this side with a force of 1.96 newtons. So what's going to be the net force? Don't make this difficult. What are you going to do?
You have
Yeah,
to,
basically subtract. You can make this positive and add that to a negative value because he always talks about the sum. But at the end of the day, what's your net force?
0.2.
0.2. So here's the deal. Here's the other way that you can view this conceptually. Is that imagine that you've got a frictionless track and you have a fan that can exert 0.2 newtons of force in this direction. Okay? And the total mass of the cart is 0.440 kilograms. So in other words, mathematically it's treated the exact same way. You taking a 0.44 kilogram mass and putting a fan on it that exerts 0.2 newtons of force is the exact same idea as saying I'm going to put a 220 gram mass on one side and 200 gram mass on the other. So here's one of the most important things. Why do we have to divide by the total mass at the end of the equation?
because
Because
force net is made up of both force applied and force opposing, and those forces are made up of the other masses.
yes. And so here's the shortcut way to answer that, is that you have a net force of 0.2 newtons that is acting on both masses. It isn't acting on just one mass, it's acting on both masses. Both masses have inertia. Both masses want to remain at rest. So I've got this relatively small net force acting on a massive system that wants to remain at rest. There's your shortcut answer. Okay, now make sure when you're calculating that acceleration that's underneath the data tables that you show me how you got those numbers, because everybody's numbers are going to be different. So right there where I say displacement and then your acceleration, make sure that I see what you did, because yours, God knows how you did yours. So if all goes well on your theoretical acceleration on this one, with the 220 and the 200, your theoretical acceleration should be around 0.5 meters per second squared. Anything else?
So,
So,
so obviously there's like different ways you can calculate that acceleration
on which one?
on these two tables.
He's talking about up here.
Okay.
Yeah, like there's two different ways, so like you would get two different values, but they're
No, 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 no. There's only one way to calculate that acceleration. That's simple, without using derived values. Go distance equals 1/2 at squared plus v naught time. What's your initial velocity? 0. You know how far it fell. You know your time. Find the acceleration that way. Because otherwise you're going to have to find some jacked up value that might be wrong, and then you're going to use that to try and find this acceleration. This is why you base it but on that.
So it'd be wrong. I mean, I got the same like value, but I just did it differently.
What'd you do?
I found the total mass, and I converted that to kilograms, and I multiplied that by negative 9.8, so that found me the opposing force, and then I found applied force by multiplying that mass times 9.8, and then when you combine the two, you get net force, and then I just divided that by total mass.
And that's your theoretical acceleration.
Yeah.
This is how you're going to get your experimental acceleration.
Oh.
There's two different accelerations that I want.
Oh.
One based on your distance and time, and then that theoretical acceleration, which is what I have you do down below.
Oh, okay. So that one would be for the theoretical, and then the one you just talked about. I had the same answer, okay.
You found the theoretical acceleration twice.
Yeah, okay, alright.
I should have gone over this yesterday and told you to use this equation. My bad.
You did.
I know I did. That was sarcasm. I know I did. Okay. Great. We'll blame it on the finger. Okay. Anything else? Once, twice sold. Get those. So for the lab today, let's start with something simple. Okay? So let's say that I've got like the smallest mass of the sets is this cute little 10-gram mass. Okay? So if you've seen this, it's the smallest one there. So let's say that I've got a 10-gram mass and it's just suspended by a string. Okay? Suspended by a string. So I want to know what the tension acting on the string has to be to hold up a 10-gram mass. So Vonda, what am I going to do to figure the tension in that string?
You have to do the gravitational acceleration, right?
Yes, that would be a cool thing to have.
So you have to take the grams and then find it in kilograms.
Yes,
right?
ma'am. By doing what?
Multiply it by 1,000.
Really?
No, divide it by, multiply it. Divide by 1,000.
Because if I multiply that by 1,000, I'm going to get 10,000 kilograms, which would be like 10,000 of these. That would be a lot. How about we divide by 1,000?
Yeah.
Okay, so let's take the 10 grams, right? And let's divide by 1,000 in 1 kilogram, which should give us 2.010 kilograms. Then what, Vonda?
Then you multiply that by the gravitational acceleration.
Beautiful. Thank God you didn't say multiply it by gravity. Okay. Which last time I checked was 9.8 meters per second squared.
Really?
Last time I checked. Could have changed.
It could have.
What if?
How long
What
ago
if
was
it did?
it?
Like, honestly.
Can we check
what if
again?
it just changed like
What
what if it
happened?
changed?
Then-
981.
Then something went
It
very
changes.
wrong.
It does change depending on how far you are from it. Like it's lower at the top of Mount Everest than it is like at that
What?
mountain. So you got-
Hopefully I can jump higher on Mount Everest.
Yes.
Go to Mount Everest. Yeah.
But you're also going to be weighed down with like oxygen tanks.
I can hold my breath for a few seconds.
Okay. Anyway, so since you all suck at mental math, I'm going to take 0.01 kilograms, multiply that by 9.8, I get what?
500 grams.
How about 0.098 newtons?
Yeah. Checks out.
Checks out, we're good, verified? Okay. So, if you want to call that negative, which we can, that's kind of cool. Then I got this upward force of positive 0.098 newtons, right? Okay. Is the system going to accelerate?
No.
No. Why?
Forces balance out.
Force
Yeah,
zero.
all the forces add up to
0.
0. Nice. Good. This should be old. Okay. Now, let's say I go in here and I just cut the string. Okay? If I cut the string. What's the 10-gram mass immediately going to do?
Accelerate downward.
It's going to accelerate. Okay? At that point, what's the net force acting on the 10-gram mass?
Negative 0.098 newtons.
Yeah, because there is no upward force. This is the only force left in town, right? That's it. There's nothing else. So if I take 0.098 newtons, and if I divide that by the mass, oddly enough, I'm going to get negative 9.8 meters per second squared, right? So if I've got this is going to be important in terms of the lab. So if I've got a 10-gram mass suspended by a string, gravity is pulling down at negative 0.098 newtons. That means the string is pulling up at 0.098 newtons. Okay? Not very much, but it's just a tiny little mass compared to the mass of the Earth itself. Got that? Okay, now, set that down. Okay, great. So, let's go to the back and I'm going to show you what's going to happen with the lab. So,
Oh, this is
come back.
4 pages.
I know. Get that Stanley bird cam. Oh wait, I'm at the wrong place. Bring in the bird cam.
Can you take that and put that on the string?
Of course. Oh my gosh, we're moving the string.
Told you.
You can tell me.
Told you.
Okay.
I did.
Okay, so I've got this cute little kid.
Wow.
New keys right here, man.
Did it just jump out of your hand?
Put it on the table and then it
Jump.
falling off.
Gravitational acceleration.
Is it like a gravity storm or what? Okay. Yeah, I don't, not,
I thought that was cologne for a second.
Huh?
What is that? Is that oil?
No, it's
It's
ferro.
oils.
It's
It's called a
ferrofluid.
ferromagnetic fluid.
Oh, mineral oil?
I drink
No.
that for breakfast. You probably should.
Oil smoothie.
Oh dear.
Four raw eggs.
Put your head in there and slam the door. No. No. Okay, I'd get fired and you're not worth it. Okay. Oh, shoot. Well, it's true. Okay.
Eli
All right.
in that case.
So here's the deal. I've got this cute little 10-gram mass on the end of the string. Okay? I've got it attached to this big massive card up here. In addition to the card, I've got a 500-gram mass, and I've got a 20-gram mass. So here's the question. Can this little 10-gram mass out here accelerate this whole system back here?
I think no. It's
Yeah.
This is gonna show.
I think yes, because
Yes.
there's
I
think
also
yes,
found
'cause this is
Yeah, you
frictionless.
read the track and it's
gravitational.
so I think yes.
I've pieced the track.
It looks shiny.
It looks shiny.
It's super green.
It'd be pretty boring
Okay.
if it did it.
So,
Yeah.
so I'll let go and we'll see what's going to happen,
Just
right?
logically.
Whoa.
Okay?
Hey, that's constant right there.
What?
Constant what?
I'm not gonna talk anymore.
Why not?
You're saying dumb
I'm saying
stuff.
dumb stuff.
Well,
No, it is.
It is constant velocity,
but it's-
right?
no.
Okay, never mind. Okay. Oh,
If it was constant velocity, well,
Does not move. Acceleration. You know.
okay. So,
I'm just making sure it doesn't.
okay.
yeah.
Okay. So, I've got a 10-gram mass out here on the end. So, what did we just establish with the gravitational force?
That was not me. I just picked up this thing because it goes to this. That wasn't even me.
Okay. So, what's the gravitational pull on the end of this 10-gram mass on the end of the string?
Negative 0.098.
Let's just make it 0.09. Don't worry about being negative later, okay? So, if I cut the string, what would be the acceleration of the mass?
Negative 9.8 meters per second squared.
No. If I cut the string,
Negative 9.8 meters
yeah.
per second squared.
Now, so because gravity's pulling down on it, right? So here's the question. When I let go of this, is gravity still pulling down with the same amount of force?
Yeah.
But why doesn't it accelerate at 9.8 meters per second squared?
Because the mass.
Pull that.
Oh, we got to drag this big thing, right?
Don't forget your little brother.
Big brother, this came out. Okay. Yeah, big
Or if
little brother.
Eli is your
Okay?
little brother.
Now, so in this situation, here's the deal. So what we're doing is that we're letting gravity provide an exact amount of force. Okay? I could try and push it with 0.098 newtons, but it would be almost impossible for me to maintain a constant force the entire time. So by putting this 10-gram mass out on the end, we're letting gravity provide the force to make this thing accelerate. Now, just like the Atwood machine yesterday, we're going to make this the force applied. Okay, so whatever's on the end of the string is going to be the applied force. What we're going to assume is that this thing is frictionless. Okay, we're going to assume that. Now, it isn't quite greased, but it is shiny. Right? So we're going to assume initially that this is a frictionless surface. Okay, so we're going to assume that there are no opposing forces. So this thing is hanging straight down. We're assuming that this is a completely horizontal system. We let go of it, we're going to get a certain amount of acceleration. So what you guys are going to do, you're going to run 5 trials. This thing needs to have a displacement of 50 centimeters. I don't care which marks that you pick. I say to go 15 to 65. I don't care. So if you come back here, like let's say you're at 20, let it fall until it crosses the 70 centimeter mark. You want at least 2 people timing it, and you want to make sure that who's ever timing it is looking at this point when it crosses it. Don't stand back over here, okay? Like don't be, if McGriddle's timing it, I don't want him sitting over here trying to guess when it crosses the 70 centimeter mark, because he's not going to be able to judge it very well because he's looking at it from this direction. So, you're here, you're going to let go, you're going to do this 5 times. Now, at the end of that time, we're going to take off the 10. I want to put it back up here, and then we're going to put a 20. Now, why do you think I took the 10 and put it back up here?
So the mass
Oh, that way I keep the mass constant, right? Okay? But now, what have I done to the amount of force that's going to act on the system? Made it bigger. Why?
because thought is smaller. And
No. There is no opposing force. This is a frictionless surface.
Okay.
But what have we made bigger?
Fat.
We made fat bigger. There's still no opposing force. Now, when I let go of it, what should happen to the acceleration? It should get bigger. So what should happen to the amount of time it takes to travel that? It should be smaller. Now when I let go of it,
Yep, that looks a little bit faster.
looks a little bit faster. So if you look at this in terms of Newton's second law says what? What'd you say? F equals ma. That's Newton's second law. It's the only mathematical one. So what have I done with the mass of the system?
Kept it constant.
Kept that constant. What have I done with the force?
Changed it.
So the acceleration.
Yeah, so I made a bigger force with the same mass. I should get a bigger acceleration. Okay? So let go of it, boom. So you're going to run this trial 5 times. Take the average time. When you get done with that, then you're going to do 3 trials on the next page. You're going to take this little block of wood like this, and you're going to put that underneath the front edge, so that gets lifted up, and then you're going to do that again with a 20-gram mass. Now, in the spirit of how I want this done, I actually want you to predict what's going to happen to the time it's going to take for this thing to travel. Okay? Then I want you to do the trials. And it's a prediction. There's no right or wrong. Okay? But you're going to have a prediction. You're going to tell me why you think that's going to happen. When you do that and you elevate this, make sure that you raise that pulley up some so that way that string is still parallel with the ramp. So whenever you're doing this, you want to make sure this string is running parallel with the ramp itself. So you're going to do 5 trials with this, with the 10, 5 trials with the 20, and then 3 trials with the 20 on the end and that block of wood underneath. Got that?
Yep.
Okay, back we go. Okay, so just so that, I'm going to make sure everybody's on the same page. So, on this 10 gram trial, notice I've got this little asterisk and it say, we're going to assume that the system is frictionless. So, for the 10 gram trial, what we're going to assume is that the weight of the 10 grams on the end is what is providing the applied force, and we're assuming that it's frictionless, so that's also the net force. So, on the 10 gram trial, here's your 10 grams, gravity is pulling down on that, was set with the force of 0.098 newtons. So on that 10 gram trial, where it says net force, that's going to be 0.098 newtons because it's just gravity pulling down on that 10 gram mass. Now, we need the total accelerated mass. So up here on the top, I'm going to tell you, determine the weight of the cart and then determine its mass. So how are you going to find the weight of the green cart? Don't make this difficult. Ethan, what's this? International sign for use of the Newton scale. Okay? Hang it up, right? Now, but that Newton scale is going to measure in what units? Newtons, hence the term Newton scale, right? So how can you take a reading that's in newtons and use that to find the mass?
Divide by 9.8.
0.8 per second squared. So you're going to take the scale, hang up the green cart. That's going to be in newtons. Divide that by 9.8 meters per second squared. Easy peasy. You're going to get the mass. But then you need to add that to the 500 gram block that's on there, the 20 gram mass, and the 10 gram mass. Okay? So that's going to be the total mass of the system. The only thing we're going to change is how that mass is distributed. Okay? That's all we're going to change is how the mass is distributed. So, on the 10 grams, make sure you have this written down. That net force is going to be 0.098 newtons. Then you're going to have the total accelerated mass. Then how are you going to get your theoretical acceleration?
That's what I did.
2D.
Yeah. No. How are you going to get your theoretical acceleration? Force net divided by
Mass.
to get you your acceleration. Now, when you're going to use the distance and the time is over here on page 2. So on page 2, the second one down, then I'm going to say determine the acceleration of the cart based upon your measured values of displacement and time. This is where you're going to use distance equals 1/2 at squared. Okay, is page 2 down over here. That's when you're going to use that. Then you got a bunch of questions to answer. Okay, that are going to require thought. Now, and whatever you do when you're answering these questions, just don't say, oh, it changes, okay, or it's different. No, if it changes, you say, oh, it's going to increase, oh, it's going to decrease, it's going to do something like that. Do not just say it changes. I will have a conniption fit, okay? Now, then on page 3, this is where you're going to take that block of wood and put it underneath the leading edge of the ramp, okay? And again, this is what I want you to discuss as your lab group. What's going to happen to that time when you put that block of wood underneath? Basically, you have 3 options. It's going to take more time, it's going to take less time, or it's going to take the same amount of time because I've still got the same 20 gram mass suspended from the end. Okay? There's no right or wrong, it's a prediction. Okay? That's just it. It is a prediction. You just have to justify your answer. Then you're going to run the trials and see what's going to happen. Then you've got a bunch of questions to answer on that. The last page is basically dealing with the same situation. If you don't know how to work the number 10, go back and look on the front page of the lab and say, wow, how did we do that as a class? What did we use as our applied force? What did we use as our opposing force? If there is one, how did we get a theoretical acceleration? Okay, I'm done. You're on your own. Now,